Hello friends, today I'd like to talk about a very exciting paper 3 questions and possible extension for the internal assessment. Today I prepared as a math genie, 방문 genie, with a gamma function and Riemann sum from November 2022 and May 2023. Okay, without further ado, let's get started. So in 2022, paper 3, question number 1 involved surface area formula, right? So they gave you the surface area and then you were not, let me remind you, you're not required to prove it using the Riemann sum. But for today, the span of the class, I'd like to engage of how to derive such formula and be able to apply to prove a certain formula that we learned for granted, things like the surface area of sphere and whatnot. Okay, and then make some possible extension for something called a double integral. And also, I like to make an association with the paper 3 problem, again from 2023 with the number 1, which involved something called the gamma function, right? So something interesting about this problem is that it didn't mention about that the fact that the function dealing with this question deals with the gamma function if you put it into the improper integral, but instead, you are required to sort of gain an insight that if you increase the value of n as a positive integer starting with 2, 3, 4, 5, you realize that you get a factorial expression, right? So if you were to use on the calculator, right, or doing the improper integration by parts, you realize a2, which was which is the integral expression from 0 to infinity of x squared e to the power of negative x dx somehow converges to 2, and 3 goes to the 3 factorial, 4 goes to 4 factorial, and 5 goes to 5 factorial. And what you had to do and make a suggestion is that this becomes an n factor. Okay, and then what you are to do is to use it to prove this by integration by parts. Okay, so yeah, so I like to make a connection between these two paper 3 problems. And what I wanted to remind you is that those amazing questions on the paper 3 didn't come from out of nowhere, from a thin air. It came actually from a very historically significant observation or the fields of mathematics back in the days. So today I like to appreciate those questions by delving into a deeper understanding of those topics and make association with your potential IA topic. Okay, so let's go. Without further ado, let's get started. So today, first, I'd like to start with the Riemann sum and surface area. Let's talk about what I mean by that, right? So we already know what it means by the Riemann sum, don't we? Because when we were to approximate the area under the curve, we use this infinitely many small rectangles to approximate the area under the curve. And as you know, the more you increase the segments, more you dissect, you realize the approximation gets better and better, as you can see in this nice animation. All right, so and then the typical formula to deal with this Riemann sum was that we were to get these, sort of a AK. Right? Imagine that I've got AK. Okay, so then I got the delta xk, and then you put that xk onto the function, right? Function of xk. So what you do is to make an approximation of this rectangle area of the rectangle, which becomes f of xk times delta xk. And what we were to do is to add this finitely many, right? So then we introduce the sigma notation, right? Which then goes from k is equal to 1 to n, whatever. And as you know, if we increase the number of terms, that means you're making the delta x infinitely small, and this is what it will convert to the integral expression of the a to b function of x dx, and that was a typical expression that we have learned from the Riemann sum, right? All right, so just a quick reminder of what you had done before, and what we would like to do is to use this sort of approximating understanding to extend to the surface area formula that we were asked to apply just only in 2022 paper 3 problem, but we would like to actually derive it, okay? Another approximation that you learn is the volume of revolution, isn't it? So for example, if I have a cone shape, but if I just sort of tilt it so that you can see from the y-axis and x-axis, so imagine that I've got the axis like that, x and y-axis. Right, then what we were able to approximate was the volume of revolution along the certain axis. In this case, as you can see, I can approximate the volume of revolution along the x-axis, right? So if I, for example, approximate the volume using a infinitesimal, in this case, it's going to be a cylinder, isn't it? So if I do the volume of revolution, then I got this infinitesimal infinitesimal cylinder, which then can be approximated by the radius of such, which can be given by the y coordinate on the function. So that I'm going to call it f of xi, right? And then the difference between the consecutive x, which we call delta x, right? For capital letter delta is to represent the difference. And now I can use the volume of a cylinder formula, right? So the typical method of deriving the Riemann sum and extend it to the definite integral expression was that we were to get the pi r squared times h is the formula for the volume of cylinder, isn't it? So that I'm gonna use this infinitesimal cylinder, approximating the radius by the y value, which is going to be pi function of k but square, and then this height is gonna be delta xk. Okay, so then I have infinite series of this following. Right, so this is how we approximate the volume of the revolution, and if you go for infinite in many of them, then you see that this is going to converge to the area of the volume of the revolution, which then we can associate this infinite expression as the sum but stretched. Right, the integral symbol is just s but stretched vertically, going from whatever the bound that you were having, pi, and then this f of xk sequence definition will be approximated by the function. And then we square this, and then this capital letter delta is going to approximate by this lowercase d is the typical formula that we know of, right? So that's no problem. However, what I like to do is now, okay, so, briefly speaking, we know how to work with the, for example, the volume of, the area under the curve or the volume of revolution using the approximation, right? So with this marvelous technique of using the infinitesimal shape that can approximate of the things that we typically know of, in such as the area of a rectangle or volume of a cylinder, and then use it for general case of a function, right? So for here of a 3D shape of the volume of revolution, what I like to do is to actually approximate the surface area. Right? Let's suppose that I want to get the surface area of this. Okay, so for the surface area, what I can do is no problem. So I would try to use something similar that I've been doing, right? So which was we're going to use another cylinder here, but instead of the volume this time, I like to use the curved area of the cylinder to find the volume of the revolution of the surface area, right? So now, instead of using the volume formula for the cylinder, I like to do the surface area. Okay, no problem. Let's do the surface area of this. Okay, and what we can do is to use the surface area of a cylinder, which then it's gonna be the curved area, where if you open the network, right? If you open the net, it become like that, and as you can see, the circumference, which is a 2 pi r, is going to be given as the length, and this delta x is going to give you the height. So then the area of a rectangle that is sort of engulfing the shape of the cylinder is going to be approximated by this, where again the radius can be approximated by the y coordinate on the function. So, right? So let me quickly give you the list of those approximations using this more neater expression as the following. So now I want you to notice this 2 pi r is the length along the curve. Length of the circle. That's going to be giving the length of the rectangle, right? That's the circumference. Very good. And I got the delta xk, which is going to represent the height. So now I got that expression of the curved area of a cylinder, and I like to do the infinite sum, okay? Because I want to induce the integral expression. So now I'm very happy because I got the infinite series formula and delta, and then I got the function of xk. So beautiful, I can just plug it into the definite integral expression as the following. So remember, the delta xk, in this case of a cylinder, right? The x went from 0 to height of the h, okay? where the y value were given to be the radius r. And on this one, then I can now apply the integral, where the function, in this case of a linear line here, will be given as the gradient as the radius over height. X is my y function, and what you can do is just plug it in there, right? So no problem. So what I can do is to take this out as the coefficient, right? And then I got the expression of the integral of the x, where you can do the power rule to integrate. So now let me plug it in, so that I got the pi rh. If you do just quickly compute the definite integral, because this linear expression. No-brainer. But here's the thing, I'm not very happy with this formula, because in fact, what you already know of is the surface area, the curved area of the cone, don't you? Because if you're given the radius and then the height, then you can figure out that slanted height, don't you? The slanted height here is going to be square root of who? R squared plus H squared by the Pascal theorem. So that I know, using the pi RL formula of the curved area of the cone, my result should have given, my Riemann sum approximation should have converged to the pi r square root of r squared plus the square. It should have converged in such way. But now, instead of having this slanted height, I had the height, right? So that's very confusing, right? That's confusing. Well, one thing I want to remind you here is that we approximate it along the x-axis, where we know then the limit of the x is going to converge to the edge, no matter what. But knowing that I have the slanted height that's going to play a crucial role for the surface area, I know that I cannot depend on the x only, because it's going to converge no matter what, whatever the expression of the small line segment you're going to get along the x-axis, it will converge to the h, instead of the slanted height, such as the square root of the r squared plus square, okay? So that realization is going to play the key role of you noticing the incorrect step of deriving a formula that you might have not learned for your potential internal assessment or extended essay topic. You cannot generate a formula that's going to be always correct, because then you are being a textbook, right? Then your examiner or your teacher is always going to engage with a question to ask you, why then would I look at your paper instead of looking at a book, right? Because in the book, in any textbook, dealing with the single variable calculus will probably give you the right explanation very concisely and efficiently. But why would I bother reading your paper to gain this insight of surface area? It's not about how much you know for the internal assessment per se. It's about how much of a personal engagement you can present to the reader, even if it's a known fact. Okay? For example, if you read Harry Potter, you already know. If you haven't read, spoiler alert, Harry Potter is gonna win. Okay? Voldemort, you know who is going to be defeated, right? We sort of know from the beginning that that's gonna happen for the general audience, right? But we still read because it's very engaging and very fun, right? And then that's what I want you to sort of have the tone for your internal assessment. You're not going to present an idea that's going to be scrapped from a textbook, but instead you're going to engage in a way to give your personal tone for the demonstration of a formula you may not have heard before, okay? So what I'm telling you here is, instead of coming up with a surface area formula just like the paper 3 problem from the 2022, you should sort of give a go. Okay, you should pretend naively that I didn't know anything about the surface area formula, but I like to use the Riemann sum understanding that I've done before, but I actually came up with an incorrect step, but then I got to give a reflection why this is incorrect. And furthermore, then you realize, you give a personal reflection why such step has been incorrect and what can be done better. Right? In this case, in this situation, the major axis that I like to do the integration has been wrong, because it's going to give you the limit of the h, which is irrelevant for the surface area formula of the cone. We need this slanted height. So what I like to do is to actually derive a formula that's going to involve this slanted height rather than the horizontal axis in this case. So that realization has been given in your paper. Then let's move on. All right, so now what I'm going to do is, okay, so I had a cone and I open it, and what I was to do is to approximate the area using the rectangle, right? We were trying to approximate this using this sort of a rectangle, which then converges to, what is it? The delta xk here converges to sort of a height, didn't it? Right? It converges to the height, and we don't like that. You see, we know that I like to converge to a slanted height, which is a square root of r squared plus h squared, where the r was the radius of the base of the cone, and the height is the height of the cone, right? So we want that. So you, instead of working with the rectangle, what I like to do is maybe approximate along the axis in a way that it's going to involve the delta, whatever the variable that you're going to assign for your slanted height. In this case, let's go with the delta s. So I'm going to call it delta si. Why have I chosen that axis? Because I know my limit is should involve something to do with the slanted height, where I'm going to associate the slanted height to be the s instead of the h, okay? Because h failed miserably according to the previous section, right? So then this sort of a shape can also probably be approximated by the rectangle, right? In this case, I'm going to call this as a polar rectangle. Why? Because, yeah, you're right. You know, if you look at this sort of a major arc, so if you look at this arc length and that arc length, obviously depending on the radius of this slanted height, it's going to have a different length, right? But if the delta is very, very small, if it's infinite small, this length and this length will be approximately the equivalent, right? So what I like to do is, okay, whatever the radius I get on that point, I'm going to call it maybe the radius I. I'm going to be given a circumference of the circle, right? It's going to sort of enroll there. And then this arc length is going to be given by the circumference given by the radius I. Okay? Then this area of the rectangle will be given as the following. It's going to be 2 pi times radius I times delta SI. And for me, that will be a better approximation for the rectangle simply because I know the limit here is going to converge to the S of the slanted height rather than the height of the rectangle. I'm sorry, height of the cone. Okay? So let's see how we can do that, right? So this is the expression that we have, isn't it? And then with this, okay, I want you to realize the reason I got this is the circumference given by the radius R. And then instead of the typical rectangle, I'm using the polar rectangle, which is merely an approximation, which is going to become very accurate as n gets to infinity. That means it's going to be infinitesimal shape, so it gets very, very small. So this delta S represents the height. But in this case, this sort of a height, we call it polar coordinate. Sorry, polar rectangle. All right, that's great. So then I got that. You know, that's a great expression. But right now, I don't like it too much because I want you to realize, you know, for the Riemann sum, if I had a delta x, I wanted to have a function of xk, which would depend on the x. But now I got the delta s, which similarly looks like that I need to involve a variable that is going to be in terms of s. But my radius now is not in terms of s. So that's a bit of a trouble, isn't it? So what I like to do is to use a similarity on the shape so that I can associate, the substitution so that I can replace the r in terms of the s. So let's go to the previous slide and then get the image of the cone and then see if we can find such ratio using the similarity. Okay, if we come back to this shape, right? So the reason I came up with the shape is to show you that I like to make a substitution between the radius and then the s, right? Radius and s, because I got the delta s already, so I want whatever the expression that I'm integrating should be in terms of the s. So I got the ri, which represents the radius of the cone at a certain point. So I'm going to call it, maybe this is xi, this is the radius, which is going to be given by the y coordinate on the function here. So that's the ri. So imagine that I went the previous x sequence here. Then I'm going to have the previous radius, which I'm going to give a subscript of I minus 1. Then I'm going to have this delta s, okay? And now, as you can see, I got a right angle triangle here, isn't it? So then, for the boundary for the initial condition here, then I was given the height here, and then the radius was r. Okay. So if you use the theta and the right angle, and if you use the sine, because I want to use the radius and then the hypotenuse in this case, which represents the slanted height, let's have a look at the ratio. So I got the sine theta here. Okay. Which is given by the r and the slanted height, which is going to be given by the Pythagoras theorem. So I got the r over square root of r squared plus. And that ratio must be preserved wherever you go in this point along this linear line. Okay, so then if I go with the ri, okay, will be, all right, given by the, the si, which is the length of the slanted height along that point. So it's going to be the si here. So using this ratio, I'm going to rearrange the si to the other side so that you can see, well, realize r over square root of r squared plus h squared. That's just the constant value, so it's independent of the I, times si will give you the expression for the radius, which we can use it for the Riemann sum expression, so that it's going to be depending on the s with the delta s. Then I can complete the integral expression. Let's see what's going to happen magically using that expression. So we came back to the previous, the initial Riemann sum expression using the delta s. It's beautiful because we used the polar rectangle, but now we were not very happy with this expression of the r. I wanted to make it in terms of the s, and we got it from the similarity on using the sign on the right angle triangle. Well, yeah, sorry, it's the typo is supposed to be r squared plus h squared, okay? And using that, I can replace the ri as the r over square root of r squared plus h squared times si. Then I like to put it back into the Riemann sum here instead of the r. Let me try to use the si, which then I can now finally introduce the integral expression, right? So this is going to be just integral 2 pi, whatever that is the constant coefficient, which we can just take out of the integral. It's going to be the s, and it's going to be ds, right? So that's going to be giving you the integral expression. Let's try to explore, right? So that is the coefficient. Now I got the s in terms of the s. But yes, I want you to check out the bound, because I want you to realize instead of the x, I use ds, right? So it's going to be another axis along the linear line, which then can give you the bound from 0 to, in this time, it's not going to be r, it's not going to be h, instead it's going to be square root of r squared plus h squared, right? So I want you to notice the different bound there, my friend. So now this is s in terms of s, it's a linear expression, which is going to give you the quadratic expression if you integrate, no problem, okay? So let's just plug it in, right? I'm going to plug that in on my definite integral here and try to evaluate the surface area of the cone. So we plug it in, it cancels out, and it beautifully gives you the slanted height that we wanted to have. Remember, the first initial attempt that I had with the Riemann sum along the x-axis gave me the pi rh, where I know that there shouldn't be the answer for the curved area of the cone. Now it's depending on the slanted height, which is a square root of the r squared plus h. Okay, so looking at this example, you realize actually depending on which axis I'm going to deal with, okay, and also the limit or the boundary condition that I have to be very careful choosing the certain axis for the Riemann sum. Okay, so this is a very beautiful example. So in the example in the 2022 paper 3 exam question number 1, what you also had to do is to apply it to a circle, you know, make a revolution, which is going to become a sphere, and then derive the fact that the surface area of the sphere is 4 pi r squared. But for that, you know, you're going to use a circle equation where the semicircle is going to be depending on in terms of x and y. But I want you to realize the formula that we have is in terms of the s. You know, we may not like it so much, right? We love dealing with in terms of x or y, right? Because those are the familiar independent and dependent variable. So instead of introducing a new axis, let's go back to the classic in terms of the x. And for that, what I can give you is the delta s, right? So this delta s was actually an approximation. It's just a line segment along the curve, any curve that was given in terms of a function, which is going to be approximated by the delta x and delta y. And then the line segment length by the Pythagoras theorem is going to be the delta x squared plus delta y squared. Voila, I have that, right? So that's beautiful. So what I can do is just to divide everything by the delta x squared, all right? Please do not mind over the typo here. It is a delta s because of the difference here, right? And that's beautiful, right? So for that equation, I just divided by everything in terms of x, and let me just then put it back the delta x squared onto the other side, like this, okay? And let's go back to the Riemann sum definition that we had, okay? By taking a square root on this. Now I go back to the Riemann sum definition, right? The Riemann sum definition was 2 pi r, okay? And then it was a delta s, wasn't it? And I want you to please remember the radius is just approximation with y, isn't it? So that I can just make that as a 2 pi yi, no problem. Well, which is going to be function of xi, no problem. So that therefore I need the delta x in this case instead of a delta s. But using this approximation and a bit of a factorization and algebra, you realize that it's going to be given by the square root of 1 plus delta y over delta x squared times the delta. You know, it's just a Pythagoras theorem, and I just did the factorization, and I just put a square root to induce this formula of such formula, and I'm very happy with it because I got now in terms of x still. But now, as you can see, it's got the different expression than the previous one, so I'm sure it's going to give me the correct answer. However, I'm not so happy with this expression because I'm happy with that because it's going to be the expression that I'm going to give. But what about this? You know, what's going to happen to this if n gets very large of the delta y over delta x? It is about the difference of x and the difference of y. And if you increase the n to infinitely many, it's an infinite many line segment. It's going to give you the infinite small shape where the line segment is going to be really, really small. And then this is the expression of the rise over run, isn't it? So it was the gradient between two coordinates, which we call it secant line. However, as n gets small, as you remember from the first principle, this is going to converge to who? The y prime. It's actually going to give you the gradient of a tangent. Well, what I'm telling you right now, it's really just a very rough explanation. If you want to present a rigorous proof on this, you have to explain a lot of things actually, And also, I'm assuming a lot of things about the convergence, but if you want to explain more thoroughly, you have to give what it means by the convergence and how can we achieve that, and do we have any condition on this Riemann sum, etc. Right? And in fact, what you had to do with this approximation of the rise of a rod is to do with something called the mean value theorem. But right now, for the sake of just the simplicity of this problem, I'd like to just tell you, roughly speaking, that this rise of a run would converge to the gradient of a tangent, because that's what we've been doing in terms of limit with the first principle. Okay? So that's beautiful. So this Riemann sum that I started with the delta S can still be given by the dx, like the previous case, which is going to give you the boundary from 0 to h. But it made it better because it started from something correct, right? Now instead of a 2 pi y, I have a 2 pi y times this sort of the arc length formula in my Riemann sum, which is going to now give the, the typical surface area formula that we saw on the exam problem, okay? So even if you got it wrong, okay, you have to show how you bounce back, okay, how you bounced back from the failure with your personal engagement and personal reflection to present something more correct, okay? But for that, you need to have a justification, how you came up with this formula, instead of telling the audience, telling the reader, I got it from the textbook. Then the reader will say, okay, why would I bother then reading your paper instead of going directly to the text paper? Probably has better explanation because it's a rigorous textbook. But instead, you have to sort of show your naivety that, oh, I am able to prove it, but I failed. But instead of whining about my failure, I looked at mathematically and with deductive thinking why this failed and how I can justify my approach using some other formula that we may or we may have not learned. In this problem here of deriving this formula, we started with the x, but it didn't work. But we went into another axis called the delta s, which is given by the slanted height. And from that axis, we realize, okay, now instead of using the rectangle that we know of, maybe we used a rectangle that's going to sort of engulf the arc length, we call the polar rectangle. Using the formula, I beautifully derived the pi rs. And not only that, I don't like the expression in terms of s, maybe I want to put it back in terms of x. And using this formula of the rise of a rod, which is going to now converge to the gradient, which therefore can be replaced by the derivative, is a formula the best way I can do. And I like to use it for further case. It can be a very nice step forward for your internal assessment. And in the paper 3 problem in 2022, what you were encouraged to do is to use this formula for proving the surface area of a sphere, that it's a 4 pi r square. And let's plug it into our formula with the circle equation with the radius of r, and see if you can derive it. Okay. All right. So this is the y, the semicircle, the positive part above the x-axis. Right. So that's the y value, and then let's try to differentiate using the chain rule. A no-brainer for this one, right? And then we just plug it into the surface area formula on this, which was a integral from the a to b of the boundary condition here. It was a semicircle going from the radius, so negative r to r. So it's going to be minus r to r. It was a 2 pi y squared root of 1 plus y prime squared dx. Right. So now I put the y here. This is my derivative, but I put in a perfect square. Then you cannot put the square root together because the square root of a, square root of b can be put together as long as they got the same power, right? So or the same exponent. So let's plug it in here. So then, that can go inside, and I did, and it can be simplified as just in terms of r, no problem. And for the r here is considered as a constant because the variable is the x, and that's even function. So it's going to be just 4 pi, isn't it? From 0 to r using the symmetry, then it's going to be 4 pi times rx that goes from 0 to r. And you can do your math with the definite integral that is going to become the 4 pi r squared. Very beautiful, very beautiful. Okay, so make sure, my friend, that you are able to use or prove initially a proof, then and use it for whatever the need you need to apply for your internal assessment. Of course, your real life example for your potential IA topic with the surface area could be not only just the sphere, but also, for example, the materials that needs to cover a flask of a water bottle or Coca-Cola, and see how much materials we often use it for for those bottles, and see how much damage it's going to cause if it's made out of the plastic and associated with some global warming, whatever. You know what to do, right? So those are the personal engagement. Those are the narrative that you can associate with something classic like this. Okay, you're not asked to come up with a brand new mathematics, but you are asked to be J.K. Rowling of mathematics. So you know the orthodox, you know the classic of math, such as the surface area, but how can I associate with the things that I observe in my surrounding? How can I associate that mathematically and derive something beautiful is the main aim of the internal assessment. All right, so then I'd like to talk about a bit more with the application of this integral expression. All right, okay, before I show you the animation, let me tell you what I mean by I'd like to show you further, okay? So we used, my friend, the integral expression, right? We used the Riemann sum and integral expression to give a surface area, right? So those Riemann sum application can be extended in the realm of the physics, right? So let's see how these Riemann sum understanding can be extended to the deriving another formula, maybe in the physics, right? So this is another typical example that people often write for the IA, and then let me quickly show you what it means. So imagine that I want to measure the time of an object descending, right? So from point A to B, I start from the point A, and then I like to go along a path and see which one is going to give me the quickest descending. So if you look at the animation here, voila, this linear line actually gave you the slowest. And my initial claim was that actually the linear line should have given me the longest duration because it's got shortest duration because it's got the shortest length, because you know about the time is the distance over speed, isn't it? But right now, instead of a linear line giving me the quickest descending, if I actually show you again, if I show you the animation again, the linear line gave actually the longest. And let's check this one again. From initial point to my destination, I have a linear line, circular arc, and a parabolic curve. And as you can see, parabolic curve was much faster. It's actually marvelous. It's actually fascinating. And we wonder why this was caused. It's another problem that you can do. Well, simply because the path was, as you can see, the speed is not linear in this case. The speed is not constant, sorry. And then the path is not constant either. So finding the time is not going to be typical, the distance over speed, right? But instead, what we can do is, okay, maybe I cannot do it entirely. That's going to be the average time. But if you want to get the exact time, maybe I would like to approximate again, right, on a very short period of time, right? In a very short period of time, I'm going to maybe, move along this arc, which is going to be the distance, and I like to divide by the speed to get the time expression, right? So here again, if it's not linear, you do not use the total distance over total speed. What you do is come up with an approximation, make it very small, infinite small, and then add infinite many, which is called the infinitesimal Riemann sum expression, isn't it? So now I'm going to derive a Riemann sum expression using for the time of descending of an object, okay? So let's check it out. So what I can do is, okay, first of all, I like to know the distance of the curve, right? So the length of the curve, it's non-linear, it's very hard to find, but I can approximate, right? I can approximate this line segment. If it's small enough, then I can approximate this with the delta x and delta y. And I can use the Pythagoras theorem, right, which we have done previously for the surface area. What you can do is to take the square root of it, and we got the expression before, no problem, right? So it's something that we already have done for the surface area. So that's my distance, all right? Then I need to divide this by the speed, right? So this velocity, where it's going to be changing depending on the location, right? But now we can introduce some of the understanding that you have from the physics or the common knowledge of physics, of science, is that the kinetic energy is equivalent to potential energy by the conservation of energy, right? So from that expression, you can derive the velocity expression depending on the y. Right, so I just did sort of a bit of a rearrangement. So simplify that first, then multiply that by 2, and then square root on it will give the velocity expression depending on the y. Okay, so that's beautiful. That's great. So I'm going to put that on my denominator for the delta t. Okay, let's check it out. So if I do that, my friend, right, so this is the expression I've got. That's the approximation of a time of delta t. But now, right now, what I like to do is to add infinite many, which is gonna give me the total time. So that's beautiful. That's beautiful because this was an infinitesimal shape, and now I'm doing the infinite area, so infinite sum, which is gonna induce the integral expression using the Riemann sum, right? So now I'm gonna have a total time. So this is gonna be the time taken, but instead of giving you just a value, it's gonna be given as expression, right? So it's gonna be given as the infinite series. If I put it into the infinite limit, then this delta y over delta x will be given by the y prime. This is gonna be delta x, and this is gonna be just a y, right? So let's put it into the infinite sum here. Then now using the Riemann sum, beautifully speaking, it's going to be giving you the integral expression of the time, right? So this is called a function. Because now my time depends on the y, the function, to represent the curve to give you the time of descending, right? So I don't know what function this is going to fit that's going to give me the quickest. But this is a set of functions. So there are infinite many expression of the shape that could give you infinite many different time. But our question is, what's the quickest? And that's not easy to find. So this is another level. Okay, that's another level of optimization problem. It's called the variation principle. Okay, which you learn in college, right? But some people write this for their internal assessment or extended essay. Okay, so again, the reason I'm talking about the Riemann sum is that it can be extended to very many different topics that you can associate with the real life, and hence use it for the internal assessment, right? So starting with the the area, volume of revolution, also the arc length, surface area. And as you can see, the descending time of the object descending, and then which is given as defined as a function, right? So yeah, use this idea to sort of elaborate if you want, if you will. I told you before, in my criterion T video, I said in 2023, I've seen so many people actually writing their internal assessment about the surface area of a bottle of a drink and how it can be damaging to our environment. I've seen so many those similar topics word by word. And what I gave sort of a premonition is that it wasn't going to be graded that greatly because there are too many people writing on the same topic. That was my initial call. But it turns out it was okay, right? It was all right to be writing the similar topic in a very similar tone with a similar language, but still people ended up getting the good score. So why not giving a go, right? If you haven't chosen your topic. But of course, this will be filtered by your teacher. No matter how good, how bad, depending on your feedback, depending on the feedback you get it from your teacher, it can be a good go or it can be a bad go, okay? So please check with your teacher first. But it's too popular, honestly, right? Whatever. But yeah, but there's a reason I talked about this Riemann sum expression, not only to give you some potential IA topic, but also to make a connection, association with a next topic of the video, which is called the gamma function. Remember, we had another paper 3 problem from 2023 in the beginning of the video. But you need this sort of a Riemann sum expression to delve into further of the realm of the mathematics. In this case, we're going to introduce something called the double integral. So the extensive sort of exploration of the Riemann sum wasn't necessary in our video, okay? But let's take a quick break and then jump into the gamma function, okay? So we're going to come back into the gamma function. Thank you. Hi guys, now let's talk about the gamma function, okay? We delve into the realm of, okay, the Riemann sum, and then how we can associate with the rectangles, and then how we can develop into the integral expression of the area, volume, arc length, and whatnot, surface area, and then the time expression of the object descending. And then today I'd like to talk about how we can then associate with a problem that was also imposed in 2023. So let's quickly remind you. Let me quickly remind you what the question was. The question was of working with this bizarre function, which is a product of the polynomial exponential decay. And then we actually not only look at that function, but also had to integrate, okay? And then what you were to do is to show that the integral of from 0 to infinity, x to the power n, e to the power negative x dx is in fact n factorial, right? So in the question part F, I think you had to prove that by induction, right? So I'd like to elaborate a bit more about this function, which is called the gamma function, okay? But yeah, we can prove this by induction. So let me quickly tell you what a gamma function is, right? A gamma function looks like this Greek alphabet gamma, okay? which is a product of the polynomial and exponential decay function, and we integrate, okay? I want you to notice for the x is x minus 1, so the n factorial would have been the gamma of x plus 1, okay? So if it's gamma just of x, that would be just n minus 1 factorial. So let's try to prove it just with the n instead of n plus 1 in our situation, okay? There are many properties of the gamma function. But let's try to prove this by induction, starting with the basic step, right? So if n is equal to 0, where the gamma of n, we are trying to prove that this is going to be n minus 1 factorial by using the definition of the gamma, where in this case, if I put 1, that just becomes a 1, right? Because the power of 0, so I got the exponential decay function, right? This is called the improper integral, where we just have to find a limit after having integrated, just like we did for the definite integral. So if you just do the definite integral here for the exponential decay function, it just ends up being 1. Right? Because if you not put the infinity on the exponential decay, that just becomes a 0, isn't it? So now I got 0. So that's great. And so gamma of 1 is simply just equal to 1, easy peasy. That's your basic step. And if I go with the n minus 1 factorial definition of the gamma function, when the gamma of n, I can now see that if I put n equal to 1, I got the 0 factorial, which is the definition of the n factorial being 0, would also be 1. Okay, so that's great. So thus the base case holds for the n equal to 1. No problem. Now let's move on to the induction hypothesis implies the result of proof. Let us assume, my friend, that the statement is true for k. Okay, and if the statement is true for k, then it becomes a k minus 1 factorial. Okay, so we need to prove that the k plus 1 would become the, the k plus 1 would become the k factorial. Now we write down, that's our result of proof, and this is our induction hypothesis. And I want you to realize for the induction hypothesis, I don't need to prove it. We are assuming this to be true. The only thing that we have to really work on is the result of proof. But it's nice to have the answer, but I cannot use the answer. So from the answer, what I like to do, okay, is to start from one side or the other. So maybe I like to start from the one side here and end up showing that it's actually going to become the k factorial. So this is what I like to start from the definition, my friend. And on this one, what I like to do is to use integration by parts, okay? I'm going to use integration by parts. Who am I going to differentiate? I'm going to differentiate this guy, and I'm going to integrate this exponential decay, and then see what evaluation I can use, especially with the induction hypothesis. So the result of proof was the case for the k plus 1, okay? That's great. So then we had the integral of the product of the t to the power of k and the e to the power of negative t, and if you differentiate the polynomial and if you integrate the exponential, what we end up getting for our formula is going to become the following. So that's the integration by parts, right? I'm going to differentiate this and keep integrating that. Just once, please. And if you send in, the t to infinity, this is pretty large function. It's a power function, x to the power of n. So base becomes infinity as n gets bigger and bigger. It's going to diverge, of course, but we've got the exponential decay. The polynomial cannot beat the exponential function eventually. So it's got the exponential decay of converging to 0. So if you put t to infinity, I'm sure that's going to converge to 0. Of course, you can prove it using maybe L'Hopital or other means of the method of finding the limit. And in fact, in 2023 paper 3 problem, you were given to use the limit of x to the power of n times e to the power of negative x is actually merely just a 0. So if you put infinity, that becomes a 0. If you put 0, that's just a 0. It just becomes a 0. And for the second term here, the product of this, where you realize, okay, now I can take out the k outside, it will be just the t to the power of k minus 1 times e to the power of negative t, where it was the induction hypothesis, wasn't it? Because gamma of k was integral from 0 to infinity of t to the power of k minus 1 times e to the power of negative t dt, which we assume this to be just minus 1 factorial, right? So I can use the induction hypothesis now for the improper integral, no problem. So let's plug it in and see what we get, okay? So that's beautiful. This is just going to become the k minus 1 factorial by the induction hypothesis, right? Which is beautiful. So then by using the recursive definition of a factorial, I got the product of a k and a k minus 1 factorial, which will become just a k factorial, as you can see. So now we prove the result, right? So that's great. So of course you have to write down the conclusion. but that's trivial. I will leave it as an exercise to you. So we solved the exam problem, right? It was a gamma function that actually becomes the product, the factorial, and we proved it by the integration by parts and also using the limit of the x to the power n times exponential decay will eventually become 0. And these are certain rules and properties of a gamma function for which I think every single line here is IA mobile, okay? Internal assessmentable, okay? Extended assayable. Okay, so those are the very, very beautiful result that you can associate with the gamma function if you are interested in the pure mathematics. And I think today we're going to have a look at the gamma of half. Gamma of half becoming the square root of pi is the aim of the lesson. Okay, so let's go. So now, okay, so gamma of n plus 1 was n factorial, but what if it becomes a rational number such as half? And now I want to show that it actually becomes a square root of pi, but then that's very, very odd, isn't it? Because I got the factorial definition of dealing with the integers, but in this time it's a rational number, but it converges to square root of pi, which is a rational number, but it's very odd. Why would I have the pi over there? Let's take a look. Sure, so what I'm going to do first, there are several steps that I need to show you, and then the first video of the Riemann sum is going to be crucial of understanding of the integration technique that we're going to do today. Okay, so let's take a look. So of gamma half, I need to show that this is actually going to be the same as I. But let's talk about what I mean by that, okay? So let's talk about what the gamma half is going to be using integration by substitution. So let's take. So sure, gamma half is going to be integral from 0 to infinity, okay? T to the power of negative half times e to the power of negative x dx. Oh, sorry, t. And what I'm going to do is to make substitution. I'm going to make the square root of t as the u. And I'm going to change in terms of u and then show you how the integration is going to go. Okay, let's have a look. So, of that integral is very typical to do. It's I got the, of simplifying the t, I got that, and the dt over du is going to be just the 2u. I replace the du on the other side. This is the expression that I've got. So for the gamma half, which had square root of 0 to infinity, t to the power of negative half, e to the power of negative x dx, t, will become the following expression in terms of u. This is by the integration by substitution, isn't it? So this is what we have. But as you can see, the u and u to the power of negative 1 will cancel out. This just becomes twice of 0 to infinity e to the power of negative u squared du, okay, which is known as the Gaussian integral, which is now can be seen on the gamma function, okay? So that's beautiful. So my job is to integrate that, okay? And then integrating that is not easy. There's no elementary function that could give you the antiderivative of this, but you can still evaluate the improper integral. It's not an easy question, okay? So we're not going to use the typical integration method that we know within the purview of the single variable. We're going to use the multivariable calculus. But let's see how we can actually solve it using multivariable calculus, which is going to be very similar. It's going to be an extension from what we had done in the first video with the Riemann sum, but now we're dealing with the 3D approximation. Let's have a look. But let me quickly show you how I'm going to do it. So, in the question that I just showed you, which is a very good potential IA or E or paper 3 problem, we define that gamma of half as the I of the following. Those I and I are given as the following, right? So that's the gamma of half each, isn't it? But it looks different, but they are the same because the role of the x here and y are just merely just the dummy variable, right? It's just guiding us, helping us integrate, and it's in terms of x and y. I'm very happy with that, right? So now let's have a look at the expression of the I squared, which I got the product of the integral, right? And it becomes 4 times the product of the integral, right? But here, okay, I got the product like that, but today we're gonna learn how we can use something called a double integral. I'm just giving you the preview. We're going to extensively go over how we can induce that, something called the Fubini's theorem, but I'm just giving you the preview of what we're going to do today. Okay? I'm not going to ask you to just accept this. Don't worry about it. But not only this, you're going to change the variable into something called the polar coordinate, right? Today, you're going to learn extended integration by substitution today, my friends. So please fasten your seatbelt and enjoy the ride of the roller coaster of the multivariable calculus. But that's sort of the start of the gamma function, and especially gamma of half induces the error function, which is also known as the Gaussian integral. And how we can evaluate is the following. So let me quickly remind you about the Riemann sum, right? It was the area under the curve was approximated by infinitesimal rectangles is how we define the integration. Okay, now we also learn about the formula with the area, volume of revolution, arc length, and things like that. But right now, I'd like to use that infinitesimal definition to find the volume under the surface. Okay, this surface. Okay, what you can do, what you can think of the surface is the set of coordinates floating over the xy plane that depends on both x and y. So it's a vector value function. So right, if you look at it, now this z coordinate is floating around the xy axis, so it depends on the x and y. So right, so the expression of the z coordinate depends on usually the function expression of x and y, things like that. And I like to find the volume, right? Of course, what we can do is to define infinitesimal shape that I can define easily and use it as an approximation for finding the volume under the surface. For example, for the area, we use a rectangle. For the volume of revolution, we use a cylinder, right? And for this one, who am I going to use? For this one, I think I can use a cuboid, right? If I go with this sort of a infinitesimal cuboid shape, okay? You realize that I need to have this, for this cuboid, I need to have a base area, which is going to be a rectangle, which is going to be the difference of, what is it? Delta y and delta x, and the z coordinate, the length, the height of the cuboid will be given by the z, which is defined as the function expression of x and y, right? So this is going to depend on the x and y. So if I have that product of f, whatever the coordinate that is, I don't know. That's the height. And then if I use the product of the delta x and delta y as an area of the rectangle, and then if I add infinitesimal in many of these, it's going to approximate the volume of the surface under the curve, like we did for the area, volume of revolution, and then the arc length, the surface area, etc., etc. This understanding can be applied for any cases, right? As long as, of course, you have to give a rigorous proof if you want to talk about this, but you get the rough idea. I am approximating first, okay? So of this region of the R, right, I can create a small tiny line segment of the X and Y, and they call it as the base area of the pillar that I'm gonna have. Okay, and if you then multiply by the Z coordinate, which is given by the surface area, surface expression of the Z in terms of X and Y, I can come up with this volume of the pillar that I can have infinitely many of it, right? Is what we're going to do. So that's a first start, okay, of deriving something called a double integral to find the volume of the curve, surface. Okay, that's great, that's marvelous. So let's see how we can use this sort of a calculus understanding for our next situation. That's great. So we're going to approximate the volume using this infinitesimal pillar, okay? The delta x times delta y will represent the area of the rectangle. So that's great. That is a beautiful. So that's the volume of a small pillar, okay? But here's how many of them should I add is the question, right? How many, okay? So let me quickly have a look at the shape again. We are now interested in how many we're gonna have. Look at this. So imagine, okay? Imagine that I start with this, let's say, the coordinate at the y1, all right? And then I'm gonna have x1 coordinate there, and that one is gonna have the same x value, but I'm going to have a different y value, so it's going to have x1, y2. So imagine that I'm going to the first row of this sort of a shape, and the next one is going to be x1, y3, etc., etc. Okay? So if I want to talk about the sum of the volumes of the first row, okay, it's going to be given as the following. Let's have a look. So it's going to be a function of x1, all right, and y1 times delta a, which is going to be the rectangle expression that I'm going to give for the dx and dy, why not, okay? And I'm going to add that for the second pillar along the first row of the x. So it's going to have the same x1, all right? But then the y is going to change of the delta a. And then we're going to go all the way up to the nth pillar in the first row. I'm going to have a function of x1, yn, delta a. Okay, so that's the sum of the, what is it, the rectangle that I have, sorry, the pillar that I have in the first row. And then, of course, I don't want to deal with all this sum just on the first row. Let's go for the second row. It's going to have f of, what is it, x2, y1, all right. And I'm going to have delta a, but now the f of x2 is fixed, but y's are changing again. Okay, we're going to add all that up, all the way up to a function of x2, y, and delta a, and then we're going to do this on and on and on, right? So we're going to have many sum here. starting with the first, second, and goes all the way up to the nth row, which I can actually, why not? Let's go up to the nth row. I'm going to have a function of x nth row, and starting with the first y value for the pillar on that row, and I'm going to go all the way up to, so now I'm dealing with this row pillar, right? And I'm going to go all the way up to f of x and y and delta a. Okay, so that's great. So from here, what I like to do, okay, is to use a sigma definition to represent this series. Okay, let's have a look at the first row expression using the sigma, using the series expression. So that can be easily given as, what is it? This will be given as a sum of f of x1, yk, delta a is what I've got, isn't it? Right, when the k is going to be from 1 to, what is it, the n. Okay. The second row is going to be same as sigma. K is equal to 1 to, well, let's go with j. 1 to n of a function of x2, all right, yj. Okay, that's great. And it goes on and on and on. This is going to be a function of whatever L is equal to 1 to n of a function of xl, xn, and the yl. Okay? But as you can see, there are n many of those sum, right? There are n many of sum, because I go from the first row up to the nth row. So then I'm going to add each sigma here that has, let's say, n many of it. Let's imagine that I got the n many sort of a column along the y-axis. Then this is going to have, it's going to add first, second, all the way up to n many. Sorry, let's call it n many y here, because I can now call the n many or m many for the x and y many row and column, right? So then it's going to be sigma, the sum, all whatever the sequence we had, but in this time the x will change to, what is it? The m, right, of y, l, okay? Sorry, well, j, k, right, delta a, things like that will be the double sigma, right? So we add x first, and then we add by the y's, okay? Is what I'm doing with the double summation here. And detail has been given in this explanation here, but really you're just adding first row and then goes by the column, and then for each row I just express it as a 1 sigma, but I have a column many sigma of that, which I can put it into the sigma sigma notation for that sum also, right? Let's take a look at this. Sure, so that's the volume, but now I got the outer sum and inner sum, and then we can combine all together to represent as the double sum, right? So that's what I have, right? That's gonna be the double sum. We add by the rows first, and within the row there's another series of the by the column many, so that's gonna be the double summation. That's what it means. You do sum of each one by one, inner and then outer. Okay, so that's what it means of the double sum. That's where you derive the double integral, because I got the double series, right? So S, remember, is the stretched out expression of the sum, S integral. So therefore, when I have this double sum of expression of the function x and y, which is the middle point, using again something called the that's something to do with the intermediate value theorem. But now, if I just assume, okay, that's just going to be the expression of x and y. That's going to converge when n goes to infinity, and this dA was defined to be delta x and delta y, wasn't it? So now I'm going to just make into the infinite series, which I can now induce the double integral. Right? Every time we have an infinite series, we just make it into the infinite integral expression derived, which we have some from the Riemann sum of area or volume or surface area. And that is the sort of very rough definition which I can give you to find the volume under the surface. That's going to be the volume under the surface of a 3D, which is something to do with the multivariable calculus, right? But that's sort of the logic here. Okay, that's the logic. And from this point onward, you're going to learn a theorem that even in college is going to be very difficult to understand in terms of proof. Okay, what I'm talking about right now, the theorem itself is very easy. You can just accept it. However, in order to prove it, it's going to be very complicated. Even textbooks don't tell you about the proof because there's very tedious and very rigorous computation. Okay, so let me quickly tell you, if you have learned double integral, what can I associate? There's something called the Fubini's theorem. Okay, if you ask me, well, what is the Fubini's theorem? Is that okay? In terms of you can interchange the x and y. It's commutative under certain condition. Okay. But of course, you don't have to know the proof of it. Even if you're writing the IA or EE, I strongly advise that you sort of talk about the insightful, intuitive approach rather than the rigorous proof because it would be very complicated. Don't do it. But what it says about the Fubini's theorem is that you can do x first or y first. It's commutative is what they claim. Okay? It's called the Fubini's theorem. And another lemma that you can associate is the following. Another lemma of Fubini's theorem is the following. If I have just a function of x and just a function of y under the surface, that I can put it as just a product, you can separate the integral just in terms of x and just in terms of y. That's a lemma from the Fubini's theorem, which I'm going to use for my Gaussian integral from the gamma of a half. Okay? So that's the lemma we're going to use. If it's just in terms of x, if it's just in terms of y, it becomes commutative. I can separate it. So how am I going to use it? Well, let's take a look. So what we had was we got the I square, and then x and y, they're just dummy variable. In fact, it's the same thing if you evaluate, right? But now, look at this. By the Fubini's theorem, now I realize this is just in terms of x, this is in terms of y, which I can put it back in terms of this double integral, right? In terms of x and y, right? So this is what we have done. Well, this typo is supposed to be y. Of course, you can do in terms of x first, in terms of y first, doesn't matter in this case because it's still very complicated, right? But this jump from this product onto this is the understanding that you gotta gain from the double integral, which came from actually the Riemann sum, right? So it was a double sigma, double summation. And from that, we realized instead of approximating the rectangle under the 2D case, this is approximation of the volume under the surface. That's how we work on this product of the integral. So that's beautiful in terms of x and in terms. But now, working with the Cartesian coordinate, Cartesian form of the rectangular coordinate, this is very complicated to integral. So what I like to do is the next step. It's called the change of variables, and for this one, we're going to use something called the polar coordinate, but something that you've been doing all the time. Remember, when you have a difficult integration, right? Let's take a look at the next example. So this is the integral that we want to do, okay? But it's very hard to do right now, so I'm going to change it, like the integration by substitution. What do you remember of the Riemann sum? We remember about the area, a volume, surface arc length, and surface area, right? And then, before we talk about the integration by substitution, what I want to tell you here is, when we did the surface area, remember, we had the Riemann sum of 2 pi r over square root of r squared plus h squared delta s, I believe, right? Yes. And that was a correction after we gave a wrong, incorrect approximation of the rectangle, wasn't it? For the sector, we use the delta x to approximate, which converts to the height, but we made a correction with the polar rectangle, right? It was a 2 pi r with the delta s that gave us the correct expression for the integral, wasn't it? And that's what we're going to do also in our double integral expression in this case. At first, all right, we use a Cartesian coordinate, but right now I'd like to use different coordinate. In this case, we're going to use also the polar rectangle and see how those double integral expression will change. Let's take a look. So for the base area, it was a square, okay? Rectangle. But I like to use a different sort of a shape to approximate the area. So for this one, as you can see, okay, right now, that polar rectangle can be given by the difference of a sector area in this case, okay? So imagine instead of dealing with the xy coordinate, which is a rectangular coordinate, I want to change into the, for example, circular coordinate, which I call it r cosine theta, r sine theta, depending on the radius and an angle on the coordinate. Okay, so if I made in the circular coordinate, what I can do is now to find the area by the radius and theta. So now I got a very big, large sector area, which I have, in this case, I'm going to have a large area, let's say, a large radius Ri, and I'm going to have a previous radius, I'm going to call it Ri minus 1, okay? We already know the sector area formula, which is in radii, which is 1 over 2 r squared theta. But now I see the difference between the larger radius and smaller radius, which now it gives me the difference of a sector, which I call it as a polar rectangle. Okay. Now I got the difference of a square, which now sort of encourages me to use the difference of a square algebra factorization. So I'm going to do the r plus r and r minus r. So that's what I have. But for the difference of the radius, I'm going to use it as a delta r. Okay. So that's great. So now I got the expression of the average of the radius, and I got the delta r. But I want you to realize now I'm trying to approximate the base area instead of the rectangle, but the polar rectangle. Okay, but of course, the approximation would get better and better if the delta r is very, very small. We are trying to create infinite small shape. So when the difference is very, very small, you realize the radius will actually become the same thing. Again, you can do something called the intermediate value theorem. Okay, but right now, so then I claim that the radius are going to be very, very similar if the difference is very, very small. And therefore, it's going to become very, very similar to twice of the radius of r, right? Because if the difference is small, the radius is going to be very, very small. Similar, sorry, same. So it becomes a twice of the radius ri, which I can divide by 2, which will become just the ri. So that's the claim I have. Right? That's the approximation of the rectangular area using the circular coordinate in terms of r and theta. Okay, so that's change of variable. Right now, instead of working with the x and y, I like to deal with the r and theta. Okay, so that's great. So now we had the double summation of the rectangular area given by the rectangular coordinate and then the height. But that approximation now changes if I use the circular coordinate, that the area of the rectangle now, instead of the rectangular coordinate rectangle, I'm going to use the polar rectangle, which will be given by the formula that we talked about. It was, what was it? It was a radius times delta r delta theta, right? Again, we got that expression from the difference of a sector, didn't we? And for the difference of the radius square, I used the a plus b, a minus b factorization, and using the intermediate value theorem that if the delta is very small, the radius is going to be eventually very same, so it becomes twice if you add them together of the consecutive radius. So this is the approximation we had for the area. So this delta area expression, which is dx and dy, will be replaced by the expression that we derived from the polar rectangle in the double integral case. So now I'm very happy. I'm very happy because all my function expression will be in terms of r and theta, and I got the dr and the theta. But I want you to realize I got this interesting scale factor r. Okay, and that's what happens when you do the function integration by substitution. For example, if I were trying to do the the x times, let's say, e to the power of negative 1 over 2 x squared dx, right? If you look at the integral like that in terms of the x coordinate, this is quite difficult to integrate unless you change the coordinate, right? That's the integration by substitution. Instead of dealing with the x, I like to deal with the u. If I had made the substitution u as a negative 1 over 2x squared, you realize du over dx is going to be negative x. So then this integral now becomes, under the coordinate system of u, becomes, eu du, which the integral becomes much more trivial than the previous stated, right? And that's what the integration by substitution is. When you have a function of u du, and then you want to convert back into the function of x, you have function of gx, but always, whenever you convert into the x coordinate, you always have to multiply by the scale factor. Right? That's the role of the scale factor that you can also see in the double integral. Just like when you are converting between the Celsius and Fahrenheit, you have to multiply the scale factor, and that's what's happening in the change of variable, in this case, from the rectangular coordinate for the base area of the surface as now in terms of the r and theta polar coordinate using the polar rectangle. Okay, so that will be also, developed further if you are keen on working with the double integral or triple integral. Multivariable calculus is something to do with the Jacobian matrix. Okay, but right now let's just leave it as it is for the double integral only. Okay, so that's marvelous. That's great. So now for this infinite series, if I take the limit m and n to infinity, will become just double integral expression function in terms of r cosine theta, r sine theta, dr d theta, but don't forget to multiply by the r. Okay, is going to be the expression that we want. Remember, this g, I define it as the product of a function with the radius r. So that's correct. That's correct. So that's going to be, double integral function of, r cosine theta, r sine theta, times r, don't forget that, and then dr theta. So we define the r times function of those polar coordinate as the gr of theta. That's why you don't see the r, but it's combined together. So that is called the double integral, but now the change of variable into the polar coordinate of the circular coordinate. If you ask me why did you change it, well, it could give you a good approximation. For example, if I ask you to integrate 1 minus x squared dx, right? And what we typically learn from the textbook is to use the x to be sine theta. We learned that. We are told to do that, right? And that's what I'm merely trying to do. when I'm trying to integrate e minus x squared minus y squared dx dy double integral, maybe it's not easy to do it in terms of x and y. That's why I'm trying to change into the circular coordinate and see if it's going to solve better, just like you did for the integral of a square root of 1 minus x squared dx. That's the inquisitive exploration you're trying to show in your internal assessment. Okay, so let's take a look what we can do for our double integral for the gamma function, for the Gaussian integral. Remember, the I was a gamma of a half. Okay, and I got that expression here in terms of x and y. Maybe I didn't like it, just like this integral of a square root of 1 minus x squared. I didn't know how to integrate that one, so I used the x equal to sine theta just like that. For that one, I don't see any integral expression that I can do in terms of x and y, so I like to change the coordinate. But when you do so, make sure you always try to multiply by the scale factor. Okay, let's have a look. So in this case, for the double integral for the change of coordinate into the polar coordinate was just radius r. Okay. Now I'm going to let x to be the r sine theta, cosine theta, and then y to be the r sine theta, okay? So I'm going to put that into my function expression here in terms of x and y, where I got the x squared plus y squared will be simply just r squared by using the Pythagorean identity, using the sine and cosine, will just come out as negative r squared, as it is. But remember, for the double integral, we always had to multiply this scale factor r, which I just did, right? But now the bounds change. Remember, we are trying to do the x and y from 0 to infinity. That's the boundary that we had, right? So that's the first quadrant, isn't it? And what I like to do right now, it was the first quadrant in terms of x and y. I like to express the coordinate in terms of the radius and theta, right? So as you can see, my radius is also going to go from, 0 to infinity. But the angle, since it's the first quadrant for the positive x and y, will be defined from 0 to pi over 2. So that's the expression that I'm going to give for my, the integral expression. Okay? So now I'm going to integrate within the r first. That's the first integral I'm going to give, right? I'm going to integrate from 0 to infinity of r times e to the power negative r squared dr, which now became actually pretty trivial if you think about. Previously, for the Gaussian integral, I didn't have the r, but now I have the r, right? Now it's just substitutionable, right? Because the derivative of the inside has been multiplied outside. If we make the substitution of u of negative r squared, things can be solved beautifully, right? So let's give it a go. So now let's give it a go. So now for that one, it's just going to be integration by substitution, no problem. If you now pluck from 0 to infinity, if you put infinity for the exponential decay, you know it becomes a 0 very fast. If you put 0, that just becomes a 1, but I'm subtracting it, so it's going to get just half, isn't it? So then it comes out as such. I'm very happy with this expression in terms of just the r, but now I'm evaluating it and it came out as just a 2. Right, but 2 just came outside, okay? But right now, it's independent of the r and theta as a constant term. It's trivial to integrate. That's just going to come out as a theta. So now, as you can see, if you replace with the lower bound and upper bound from 0 to pi over 2, it just becomes a pi over 2. If you multiply by 2, it becomes just pi. Very good. So now, I was defined from twice from 0 to infinity of e to the power negative x dx was the gamma of half. We show that by using the substitution of a square root of t to be u. And that one now just happens to square root of pi. It's a beautiful, beautiful result using the double integral and change of variable, which is very similar to what you just learned of the Riemann sum. Okay, and furthermore, integration by substitution, you always have to multiply by a scale factor. In this case, the scale factor changing from the rectangular to the polar, ripping the r. Okay, that's good. That's beautiful. That's great. That's the gamma function, right? So that's the gamma function, the extension that you can do for your potential IA or E topic. So that's great. That's the result of it. Okay, so that's okay. But what I like to do develop further is now you know the result of that gamma half is a square root of a pi. How can I develop that further into another idea in mathematics, which is often used a lot in probability statistics or algorithm or computation, which is called Stirling's formula, right? So the large value of n factorial can be approximated by the following expression. But if you look at the expression, why do we bother using this expression for a very large value of n? Is that the n factorial is a recursive definition, which can be hard to compute if n is large, because you got to do one by one. For example, if you want to do 1,000 factorial, you need to have 999 factorial, and you gotta have the previous one, etc. So even for computer, it could be difficult to compute. But if you give expressions such as the exponential and power expression of that factorial, computer can compute much faster. And this type of fast algorithm can be also applied for statistics to compute. Okay, so this introduced efficiency. So even though both of them obviously is an expression for the divergence, which one is easier to compute is the essence of this approach. But we can prove this mathematically using the result that we just proved. We just derived that the gamma half is the square root of pi. Let's give it a go. So now the gamma x was given to be the following, right? Which was the x minus 1 factorial, wasn't it? So if I do the x plus 1 factorial, that's gonna be the n factorial. If I let the x to be the n, okay? But right now, I give you a very bizarre substitution. My substitution here is x plus u times the square root of x. And if you ask me, how did you come up with it? Well, it's usually given in the question, okay? So just accept this substitution. And if you are given this substitution, how would you like to change your form is the things that you have to consider when you're solving a problem, okay? So let's try. So now I'm given the substitution here. So let's try to change everything in terms of u, okay? So I differentiate it with respect to u, but I want you to realize x is just a constant in this case. So if you differentiate with respect to u, x cancels out. That's just my constant coefficient. So if I differentiate u to the power 1, it just becomes 1. So that's why I get the square root of x only. Again, here I'm considering the x as just a constant. Okay, I'm not doing things like the integrating factor. Okay, that's great. So now remember, my lower bound, upper bound for the improper integral was from 0 to infinity. But now I'm trying to do the integration by substitution. So of course things has to change for the bounds also. Now I got to change for the boundary of the u. So if t is a 0, then you realize u has to be negative square root of x. So if you multiply these two, it would come out to be negative x. And if you sum together, it would become 0. So that's my lower bound. If you send t to infinity, then u has to go to infinity also. So then this is my lower bound, negative root 2 of x. And then the upper bound is going to be the infinity for the integral expression in terms of u. But right now, this is actually bothering me because the whole point of doing the integration by substitution is so that it can induce simple expression to integrate with. But now it got way more hideous. Minus integral that I have to evaluate. But let's see how we can simplify further. Well, I'm trying to integrate with respect to u. So things like the expression in terms of x can probably go outside because it's an independent term of the u. Okay, so maybe I can take him outside. Maybe I can derive some expression in terms of just x only from that highlighted part so that I can take him outside. Okay, take him outside so that I can only focus on the integral with respect to u. Okay, to see if it's going to give me any easier solution. So this is what we had. We know that that's going to be n factorial. We already know all that if x is equal to n. And then we made a substitution to simplify this in terms of u. And I'm trying to take everything out that is not in terms of u as sort of a coefficient. Okay. But before I do that, in my first binomial term here, I try to factorize everything in terms of the x. Okay. So if I did, I get 1 plus u times 1 over square root of x to the power of x. Now I take the power on both term here. I'm going to have x to the power of x. 1 plus u over square root of x to the power of x is what I've got. Okay, that's beautiful. That's beautiful. And from here, what I like to do is everything in terms of x, I would take them outside, such as, well, this was exponential, so I just use the property of exponential. If it's a sum, then I'm going to just make it as a multiple. So here, anything in terms of x only, such as this, that, and that would go outside because I'm trying to integrate just in terms of u. Okay, so that's great. Now let's go into the next line. So everything in terms of x will go outside as we already have discussed before. So now I got the expression of the u or u with the x together. Of course, that cannot just go outside, right? But now, it's a bit of typo. Sorry, it's supposed to be infinity, right? Okay. But now, now I got the product of exponential and binomial. Maybe that's not such a nice thing to discuss because that's not exponential, right? If I'm dealing with the exponential with the non-exponential form, the algebra can be quite complicated, right? Maybe I can make arbitrarily base of e and then probably put it into the power and see what sort of a combination I can make if I can have the same base, and that's my aim. Let's try to see what my aim can play. Infinity, please bear that in mind. All right, so anything that is not in terms of u, I took him outside, so I just rearranged to the left-hand side so that I can just purely focus on my integral. But as I've discussed before, this is not the base of e. Maybe it's difficult to integrate with. So please remember, if I have a, using the property of function inverse function, would be same as e to the power of ln a. That's what I've got. Okay, so this binomial expansion here is my a. So I can put e to the power of 1 plus u over square root of x to the power of x. And if you ask me why do you bother, well, now by the property of log, the x could go outside, and maybe I can multiply together with the exponential function that I had before, so that I can work things out for the integral, right? Why not? Let's try. So this is the expression that we have. Now I'm using the property of log. The x came outside. That's great. Now let's try to multiply. Well, but still, it's now okay. To simplify further, instead of just write down e to the power, I just used to introduce the expression of the exp for the exponentiation. Now I have to deal things out within this. I multiply by the exponent, so we add the exponent, right? That's no problem, okay? But, I'm adding it. You see, I'm adding it, my friend. I'm adding it. Before I continue, you tell me. I want you to pause the video and what sort of a deductive thinking you want to give to simplify further, which you actually often saw in your Maclaurin series of practice. You're right. You're often asked to find the limit, for example, or the easier expression of the series or integral differentiation using the Maclaurin series. That means you often add things out or cancel things out or subtract things out so that you cancel out several crucial terms. Right now, I got this a single term here. I got the product of x and logarithmic expression, which I can actually introduce the Maclaurin series of log, where I'm going to substitute everything with the u of square root of x as long as it's within the interval of convergence. So that's actually a worthwhile attempt, worthwhile trying to introduce Maclaurin series expressions so that if I can see any cancellation in between the terms. Let's give it a try. Let's take a look. So this is what we have. So then this was the integral expression that I had, and let's see how I can simplify. So I got that form here, I got this form here. Maybe for that one, let me quickly remind you of the Maclaurin series formula of the logarithmic term, where you should memorize the interval of convergence as well. It's an alternating term. It's very similar to the exponential, but I don't have a factorial on the denominator. No problem. So on omega, I'm going to substitute the u of square root of x. Let's try that. If you put that in the power of 1, 2, 3, 4, I can simplify the expression as the following. This is just a substitution. This is just substitution of the Maclaurin series of log when the omega, the variable that I initially had, is replaced with the u of square root of x. That's just expansion. I'm just using the Maclaurin series. And then if you now multiply by the x, right? If you multiply the first term by the x, okay, it just becomes a square root of x. But I'm adding it, as you can see, it just cancels out. That's actually quite beautiful. So let's see what sort of a cancellation we can do. So now this is all the expression that I had. But now if you multiply by the x, before we do that, remember, I'm trying to integrate from negative infinity to the, negative square root of x to the infinity. That's what my initial integral was. Please forgive me about the typos. So it was from negative square root of x to the infinity, but the initially was from 0 to infinity, wasn't it? But then that was for the variable in terms of t. But I made a substitution with a very bizarre looking substitution, which was now substituting in terms of u. So the bounds changed for the variable of u. That's why we had negative square root of x to the infinity. But now, by using the property of integral, which you can separate the region as long as it's connected. So for example, if I go a, b to c, integral from a to c is going to be integral a to b plus integral b to c, right? So that's a typical integral expression that we can separate as long as the bound is connected. So that's what I'm going to do. From negative square root of x to infinity, I'm going to go from negative square root of x to positive square root of x, and starting from positive square root of x, I'm going to send it to where? Infinity. So I separate the integral into two different parts for the betterment of computing here. What's going to be easier to compute is what we want to do. Remember, our aim here really was to find a large approximation for the large n factorial. So remember, the n factorial was given to be the, what is it, n plus 1 gamma, right? Well, that was a definition of n factorial. So I'm going to send x to a very large value here, my friend. I'm going to send x to a very large value in this case. I'm going to take the limit x to infinity because I want to see the asymptotic behavior for the Stirling's formula. So x is going to go to the infinity here. So square root of infinity will diverge to infinity. But now, as you can see, this is just the integral from the same bounds, where you know it's going to give you 0, isn't it? So the second term will just trivially become 0, no problem, because I'm integrating from the same bound to the bounds, which goes from infinity to infinity. Okay. So the only thing that I have to work on is the second part, sorry, the first part here. Right? That's the integral that I only have to work with, which we kind of saw right on the previous question, that if you now use the Maclaurin series of logarithm, and if you do the distribution of the x here, right, the first term of the Maclaurin series of log multiplied by the x will give you u times the square root of x. For second one, it's going to be minus u squared of 2. And starting with the third one, everything will have in terms of x in the denominator, right? So it's going to have plus u cubed over 3 square root of x. And then the next one is going to have, what is it? It's supposed to be 3, by the way, sorry. Minus u4 over 4 times x. Goes on and on and on. But if you send x to infinity in this one, my friend, right? What you realize is that this is a u cubed over 3 times square root of x, where if x goes to infinity, that's constant, whatever the u value that was, this will go to the infinity for the denominator, which becomes just 0. This will become 0. So all the remaining terms after the third term will become just a 0, simply because it's got the x expression in the denominator. And I'm sending x to infinity for the asymptotic behavior of my gamma function. And thanks to my initial term, it actually cancels out with the first term with the initial term here. So I'm just left with here, my friend, as what? This integral is just going to be negative square root of x to square root of x. Well, I'm sending x to infinity, isn't it? So if I send x to infinity, this is going to be negative infinity to infinity. Okay, that's beautiful. And now I'm going to have e to the power of just the one term left, which is a minus u squared over 2 du. Okay, which is very similar to the gamma function that we did from the previous section with the gamma half. Okay, let me give you a neater sort of a template here. So yeah, as you can see, this becomes e to the power of negative u squared over 2 as x goes to infinity. Simply, second one, because it's got the same bound, just a 0. For that one, using the Maclaurin series, we saw many terms canceling out. Only term either cancels out, or well, not many terms actually, only one term cancels out, isn't it? And the other one will just converts to 0 if I send x to infinity. So I'm just getting this exponential decay with the u squared, which is known as the Gaussian integral. So that's the expression that I have. Remember, right, the gamma half, okay, if I remember correctly, okay, don't get me wrong here, it's a twice of 0 to infinity, all right, e to the power of negative x squared dx, which would prove that it was a square root of pi, okay? So now that one, my friend, is going to go from 0 to infinity of e to the power of negative x squared dx. It's going to root to pi over 2, okay? And imagine that I was trying to do from 0 to infinity, e to the power of negative x squared over 2, right? Imagine I was doing that. I want to use this result from the, what is it, the gamma function of half. Okay, which we proved using double integral, change of variable, things like that. But here, okay, so maybe I want to make into the form of that, right? I want to make into the form of the minus x squared, but I got the bizarre half here, that dodgy half. I need to get rid of it, maybe using the substitution. So what I would encourage you to do is maybe I will make the u as a negative x over square root of 2. Then you realize that u squared, sorry, just positive, it's good enough, right? U squared will be x squared over 2. Okay, that sounds very nice to me. So now, if I change this integral here with respect to u, well, you know, the 0 was for the x, the infinity was in terms of x. So if I let x to be 0, u is going to be 0. And then if you put x to infinity, u is going to go to the infinity as well. But now, everything in terms of u will become the following. So x squared over 2 will be just u squared, so I got the negative u squared. And now let's try to do the du over dx. Du over dx is just 1 over square root of 2. So therefore, dx will be root 2 du. So then, dx will be replaced by root 2 du. Okay? Okay, that's actually quite beautiful because we had the result of e to the power of negative u squared, just dummy variable, it's going to have the same result. I got the square root of pi over 2 times the square root of 2. That is actually great. That's evaluation of that integral from 0 to pi, 0 to infinity. But if you look at this function, that's an even function, isn't it? Right? Because it's, if you put plus minus x, it's going to be still the same thing, and it looks like exactly like the normal density function. And now I'm going from 0 to infinity, which gave you this value. But because of a symmetry, if you go from negative infinity to infinity, we just have to multiply by 2 on that one, which just end up being square root of 2 pi. So thanks to the gamma function that we proved, we can actually evaluate this nice integral for the help of the Stirling's formula derivation. So let's take a look at the further step. So yes, that will be square root of 2 pi, thanks to the result that we already talked about before. So therefore, if you rearrange back into the right-hand side, the asymptotic behavior of the gamma function when x becomes a very large will become as such. But now, I want to sort of deal with the factorial. Now you can replace the x with n. So if I did, the gamma of n plus 1 was defined to be the n factorial, which we actually proved by the induction. It's going to give you this approximation for very large, relatively large volume of the n as the following. It's known as the Stirling's formula. And then we can actually make a little bit of more of an algebraic simplification to make it even prettier. So now, as you can see, this is a great result because now the factorial can be approximated by the power function as well as the exponential function, right? So that, my friend, is called the Stirling's formula, right? That's an approximation for the n factorial. And if you tell me why do we bother with the Stirling's formula, well, it can give you a very large value of n using the more familiar function that you can use, such as an exponential power, and computer prefers that. If you actually put it into the the programming, you can see. I think there's a very easy practice online available using the Python to compute the factorial versus the Stirling's formula and how fast it can actually how much faster it can compute for you, right? Powers and exponential. And then yes, you can also associate with something called the in statistics, you can also associate this large value approximation using it for something called the center limit theorem, which is largely to do with the normal distribution. But yeah, so, as you can see, all those beautiful paper 3 problems actually has a reason of a historical aspect of mathematics. They don't just give you those problems for you to suffer. All those paper 3 problems starting from 2021, it's worthwhile looking at because every question, let me guarantee you, is really content. It's content with topics of IA or extended essay. So please, if you haven't chosen your topic, I think you should give it a try. You should give it a try to find some topics from paper 3 because it's got beautiful topics. And for today, I wanted to talk about some specific paper 3 problems from May 2003 and November 2022 to associate with something called the surface area formula and gamma function. As you saw the connection, we learned extensive method with the Riemann sum and how rectangle, cylinder, line segment, and surface area can play the role of deriving a beautiful formula. We also saw the expression of the time descending, which was called a functional, right, set of a function. And then also we extend that idea from single variable calculus to multivariable calculus. I want to approximate the volume under the surface, and then using that sort of a cuboid, the pillar, delta x, delta y, times the function expression of x and y could give you the double integral expression. Maybe the integral that I'm trying to derive for the gamma half was not so easy, so I came up with some sort of a substitution. But for that, I had to justify why we had to multiply the extra r. And doing so, we derived the gamma of half to be square root of a pi. Not only that, have we also derived the Stirling's formula, which is a very beautiful asymptotic behavior of the n factorial. And you can extend that idea further for your own benefit. But I just wanted to go over this nice idea from the paper 3 because I just wanted to appreciate the effort put by the examiners, okay? So should I have more topics to discuss for the potential paper 3 IAE topics for mathematics, I will continue to do so. So please enjoy the videos, okay? That's pretty much it for me today. I will see you. Thank you.